Yesterday when I wasn't here, you guys watched one of my podcasts on Coulomb's law and the torsion balance experiment that led to Coulomb's law. Let's spend a minute reviewing the torsion balance experiment. If you remember from Physics 20, we had a similar experiment, a similar torsion balance experiment, but that was used for gravity, Newton's law of universal gravitation. Real similar to the one that was used in Coulomb's law, except that instead of having two masses hanging from the end of a string, we had, with Coulomb's law, two charges hanging from the end of a string. We'll call this one charge 2, charge 1. This one, it doesn't really matter what it is. It doesn't even matter, in fact, if it's actually charged. It just has to be the same mass so it doesn't tip over, so it's balanced. The second charge is going to be my fist. When I bring my fist towards charge number 1, then it's either going to attract if it's opposite, because first law of electrostatics was opposites attract, or it's going to repel if it's like charges. So if it's both positive or both negative, it's going to push number 1 away. The bottom line is, as we said yesterday, by the amount of twisting of this string, we look at how much the string turns or twists. And from that, we can determine what the value of the force is. So we got the magnitude of the force of attraction or repulsion. We know what the force is when I bring charge 2 nearby charge 1, simply by measuring how much the string twists. Well, we can measure the distance that separates charge 1 and charge 2, my fist and charge 1 there, simply by using a ruler. So we got the value of r, the distance that separates them. We also kind of have the value of Q1 and Q2. Coulomb, who performed this experiment, didn't know how to measure the exact value for charge. In fact, we didn't even have the unit for Coulomb. It was only after this that we had the unit for Coulomb, because obviously he doesn't get a unit named after him before he's done anything important, right? So he does this experiment, Coulomb does this experiment, doesn't know how to measure the exact value for charge, doesn't even have the unit for charge, but he is able to measure the relative value of charge. Let's say that this first charge, Q1, we called Q. Just as a value of Q, whatever that is, 10, 20, 6,000, whatever. If I touch it against something that's neutral, then 0 and Q both become 1/2 Q. Add them up, divide by 2. So it becomes a 1/2 Q. And then I touch it against something that's neutral again, it becomes a 1/4 Q. So again, it becomes an 1/8 Q. Again, it becomes a 16th Q. So I'm able to manipulate the value of either one of my charges, charge 1 or charge 2, simply by touching it against neutral objects. We're able to manipulate the value, not knowing what the exact value in coulombs is, but knowing what the relative value is. It's either Q or a 1/2 Q or an 1/8 Q or a 1/4 Q or whatever. Bottom line is we're still manipulating Q1, still manipulating Q2. So Coulomb performs 3 experiments. The first one, he changes the value of Q1. It's Q, and then it becomes a 1/2 Q, then a 1/4 Q, and so on. The responding variable there, the manipulated variable is Q1. The responding variable would be force. How much does the string twist in response to that? Plots a graph of F versus Q1, gets a straight line. Hey, by the way, quick question. If we're manipulating Q1, you guys have done a couple of labs now, so you guys should be good with identifying these variables here. If we're manipulating Q1 and the force is responding to that, then what are our control variables? What do you got to keep the same here? Good. You got to keep R the same, obviously. Otherwise, whatever effect is illustrated on that graph, what caused it, Q1 or R? We got to keep R constant so we know it wasn't responsible for this graph. Okay, we also got to keep Q2 constant as well. Plot that graph, we get a straight line. That tells us that the force here, the magnitude of the force, is related to Q1. As Q1 goes up, F goes up. As Q2 is tripled, F is tripled. Next little experiment he does, he manipulates the value of Q2. And still sees what effect that has on force. When he plots that graph, gets a straight line again. Tells us the relationship between F and Q2 is also linear. As Q2 goes up, then F goes up by the same amount. What would be our control variables here? Manipulate Q2, F responds to that. Tyler, what's one control variable there? Good, R. And what's the other one? Q1 this time, right? Good. Finally, he's got one more experiment. One more experiment here. F versus, this time it would be F versus R. This time he plots the graph and gets a significantly different shape. Looks like this. This time the relationship is not linear. As R goes up, F doesn't go up. As R goes up, F goes down. In fact, it doesn't even go down linearly. It goes down quicker than that. F is not related to R. F is related to 1 over R squared. So he puts those together. F is related to Q1, and it's related to Q2, and it's inverse related to the square of the distance. And we get something that looks like this. But if you know anything about proportionalities from your math class, okay, when it's proportional to Q1, Q2 over R squared, it's equal to a constant times that value. This is Coulomb's law. Now, what's the value of that constant? It's the same every time. What's its value? 8.99 times 10 to the 9 Newton meter squared per Coulomb squared. Chantal missed yesterday. Chantal came in this morning when I was asking me about this. She said, I copied down the notes, but I haven't seen the podcast. She said, it kind of reminds me a bit of what we did last year with Newton's law of universal gravitation, right? Gm1 m2 over r squared, and the torsion balance experiment there. And she nailed it on the head there, okay? Perfect. Okay, what does it remind us of? Newton's law of universal gravitation. Not kq1 q2 over r squared, but rather gravity would have been gm1 m2 over r squared. Real similar equations, right? Real similar equations, except instead of charge, we got mass. Okay, instead of k, we got g. The value of g, if you remember from last year in Physics 20, was 6.67 times 10 to the minus 11. Newton meter squared per kilogram squared. You see that the new one that we just learned yesterday, Coulomb's law and Coulomb's constant, is way bigger than the gravitational constant, like 10 to the 20 times bigger, right? 10 to the 9, 10 to the minus 11, it's 10 to the 20 times bigger. We think of gravity as being this really, really big force. Right, you're on a playground equipment, you step off the edge of the playground equipment, you fall to the ground. It's got to be a big force to pull you to the ground, right? Well, it's a big force because you are big. The Earth is big. When you're dealing with really small things, the value of the force of gravity is ridiculously small. We think gravity is a big force, but compared to other forces, like the electrical force, it's actually pretty small. Okay, all other things being equal, Fe will be dramatically bigger than the force of gravity. All right? We had you work on a few questions yesterday while I wasn't here, but the first one that we had you work on was this one on page 530. We were simply asked to find the force of attraction acting between these two charges. Hey, first of all, how did we know that was a force of attraction, not repulsion? Just by reading the question, how do we know it was attraction, not repulsion? Alex?
We knew that there was opposite sides or opposite.
Perfect, perfect. Opposite charges. Okay, this is not a mathematical calculation to answer that question. Okay, on Monday, we talked about the 3 laws of electricity. Opposite charges attract. Those are opposite charges, got to be attraction. How do we solve this? K Q1 Q2 over R squared. What did I say in the podcast yesterday was important to do when plugging in the values of charge? Yeah, drop the negative. You might think, well, why would we just drop the negative? Think about this. When we're plugging numbers into an equation, up till now, negative has always meant left, south, down, something like that, right? Direction. If we start making negative mean a type of charge, not a direction, then we're just going to get messed up with this, right? If we have negatives meaning two different things in the same question, okay, we're going to completely mess this up. Drop the sign of the charge. You need to know what the direction is. Just look at the question. You guys told me it was attraction because it was positive and negative. We don't need to do a calculation to figure that out. Okay, we don't need to plug a sign of a charge into an equation for that. Look at it. So for us, it's going to be 1.6 and 1.6, both positive. And of course, you want to make sure you're in meters, which we are there. Are we good with that question? You guys worked on this yesterday and probably okay? Hey, what's the difference here in question number 10.2 compared to 10.1? Says, hey, same two spheres touch together, return to the same distance, same two spheres, same distance. So this question is almost identical, right? What's different about it? What's different about it? Michael, was your hand kind of fluttering to go up there? Yeah, they're touched together first. This is a then. This is a then question. This happens, and then this question happens. It's like two separate problems, right? Solve the first one, and then solve the second one. What do you do for the first one, Michael, if they touch each other? Right. So let's do the whole balancing thing. Add them up, divide by 2. You did that on Monday, right? Add them up, divide by 2, balance out the charges. And then, let's do Coulomb's law at that point. F is equal to K Q1, Q2 over R squared. Just be careful here that the charges that you use are the new charges. Okay, we talked a lot in our last unit as we were solving momentum problems about things that we should think of when we read questions. Things like red pen. Okay, anything we should circle with the red pen. Things like big picture, what do we know? Not our givens, but big picture kind of generally, what do we know about this? Things like, is there 2 dimensions? Is there 2 dimensions involved? Okay, one of the things that I'd probably circle with a red pen, or at least draw attention to in some way, is the word then. Because that always tells us we're going to do something, and then we're going to do something else. In this case, we're going to do this, and then we're going to do this. Don't try to combine it. Okay? Are we okay with that question? Yeah, good. All right. The next thing that we saw was 3 charges in a row. We got, let's say we have charge 1, we have charge 2, and we have charge 3. Let's say this is 1.5 meters between 1 and 2, and let's say this is 1 meter between 2 and 3. And let's say this is 2 coulombs, 3 coulombs, and minus 5 coulombs. Those are big charges, by the way. There's a good chance you won't see a question involving charges that big. Usually it's microcoulombs, something like that. It's okay, though. We want to find the net force on number 1 here. The net force on number 1. It's a physics 20 problem almost. Let's draw a free body diagram. That's what you did in physics 20 when you had more than one force acting, right? Draw a free body diagram. Remember those elevator problems? The guy's accelerating upward in the elevator at a rate of 2 meters per second squared. Remember we had the force of gravity acting down on the guy, and the normal force acting up on the guy. Right, remember that? Remember this in the circular motion questions where the roller coaster cart is at the bottom of the hill, gravity's acting down, the normal force is acting up. You guys remember those questions? You got a free body diagram showing, you draw a free body diagram showing all the forces. That's what we want to do here. So let's look at 1 and 2. 1 and 2 are both positive. They repel each other, right? That means 2 is going to push 1 to the left. Right? 1's positive, 2's positive. 1 gets pushed away from 2. What happens to number 2? It gets pushed away from number 1. But I don't really care about that, right? What am I asked to find? The force on number 1. So even though there is a force on number 2, it's not relevant to me. What about 3 and 1? Opposite charges. Opposites attract. Right, good. That means they're going to be pulled together. 1 will be pulled to the right as a result of number 3, force of 3 on 1. 3 will be pulled to the left towards number 1, but I don't care about that one either because I'm trying to find the force on 1. All right, get these forces. K, Q1, Q2 over R squared. K, Q1, Q3 over R squared. Get those forces. And then do what you did right here, back in Physics 20. The net force is the sum of the forces. Just add them up. What do we got to be careful of there, though? What do we got to be careful of? Hey, we've already done something to help us to be careful of it. Justin, what is it that we got to be careful of? Yeah, probably going to make F21 negative because it's to the left, right? We're reminded of that because of my diagram. My picture shows it to the left, right? Make sense? All right, good. Any issues on page 533 with number 1? I'm not even going to ask you about number 2 because I know you're going to have issues with number 2. Number 1 is a question that is absolutely fair game for a unit test or a diploma exam. In fact, I would be very, very, very confident that you will see a question like number 1 on an exam. It's a virtual certainty. Hey, you know what? When I see a question like that, I'm like, whew, thank you. We can nail those questions, right? They're not hard questions. You just got to pay attention, not make silly mistakes. Okay, not bad questions. Number 2, on the other hand, good news is we probably won't see one that's that challenging, but it's possible, but unlikely. Question number 2 looks like this. We got a charge of, number 1 is negative 2.50 times 10 to the minus 9 coulombs. Number 2 is, it's over here somewhere. I don't know where it is. It's in between 1 and 3. 2 is a charge of positive 1.50 times 10 to the negative 9 coulombs. And 3, over here somewhere, has a charge of negative 1.00 times 10 to the minus 9. I don't know where number 2 is, right? We're not told. We just know it's in between somewhere. So that distance that we were given, 1.5 centimeters to the left, to the right of it, the only place we're going to use that is to label the entire distance between 1 and 3. Right? It's this distance, 1.5 centimeters, plus this distance, 2 centimeters. Where charge number 2 is in between, we don't know. 0.035 meters, right? Red pen. Always be thinking about the red pen. So far, so good? Is that good? All right. Let's draw a little free body diagram here just to make sure here. Charge number 2, it's positive. Charge number 1 is negative. 2 is pulled towards number 1. It's attracted towards number 1. 2 is positive. 3 is negative. 2 is pulled towards number 3. So there's force in each direction. Okay? Listen, if it's going to remain stationary, if it's going to have a net electrostatic force of 0, forces have to be opposite to each other, right? This is the perfect question to come back and ask one of the things that I asked you a lot in momentum, and that is, what do we know about this? Not what are our givens. The givens are the easy part. What do I know about this? Read the question and tell me what you know about this. Okay, Alex nailed it here. We know. What do we know about this? We know that if the net force has to be 0, then we know, as Alex said, that those two forces have to be the same. Okay, what do we know about this? This isn't a given thing. Okay, this is a Let's take a step back, look at the big picture. What do we know? They've got to be equal and opposite forces. Now, we don't really care about the direction there. Let's care about the magnitude. But if we know, as Alex said, that those forces have to be the same value, then make them equal to each other. If we know that, then why wouldn't we write that down? If we know that, why wouldn't we say that? F12 is equal to F32, right? Does that make sense, guys? This is a hard question. This is a hard question. But we can all start somewhere. Listen, if we mess up on it later on, I'm okay with that. Okay. But we can all start somewhere with what we know. All right. See if we can go any further with this, okay? If you got this far, hey, I'm happy with that. But let's see if we can go further. What's my next step? Michael? Cancel what? From where? I don't even see a Q2. Okay, there you go. Good. Write my equation. Good. So let's say F12 would be K Q1 Q2 over R squared, right? And 32 would be K Q, right, over, oh wait, something seems wrong about that. Something seems, not wrong, not like you're wrong, shame on you. But something seems just bothers me a little bit to say that. Why? Like, what do you think bothers me about saying KQ2, Q3 over R squared? Alex?
Well, we're trying to solve for R squared.
Okay.
But we're given the whole distance.
Yeah.
We should probably go at 0.0350 minus.
Good. Look at what we just did, guys. We just called this R. The distance between 1 and 2, right? If that's R, then the distance between 2 and 3 isn't going to be R either, right? Unless it just happens to be the same distance, which could be, right? But we don't know that, so we can't assume that. So instead of saying it's R, it is the distance still. Remember we said back in momentum, in our momentum unit, said we're doing variable value changing. We said, we write down an equation. Okay, momentum is not P, mass is not M, velocity is not V. We represent velocity by V. We represent mass by M, right? We represent the distance here by R. We represent the distance here by 0.035 minus R. That makes sense? You know what? That's a tricky step right there. Okay? That is a tricky step. Michael, what were you saying before a minute ago? Canceling something? Oh, okay. Cancel Q2 and K because it appears because they both appear in both terms, right? Okay, good. That simplifies things. We don't need to cancel those, right? But it makes it less ugly if we do. What's the value of Q1? 2.5 or negative 2.5? Kathleen, what's the value of Q1? Positive or negative? It's negative, right? Do we plug it in as negative? No, we drop the negative always, right? Over R squared equals, what do we got here for number 3 is also positive. Drop the negative, right? 1 times 10 to the negative 9 coulombs over 0.035 minus R. All right, that's kind of ugly, isn't it? Oh, wait, you look excited about something.
Okay, would it be bad to say that you could cancel out the 10 to the negative 9 as well?
Oh my goodness, it's like you're psychic here. I was going to ask you, is there anything else we could do here to simplify this a little bit? Do we need to do that? No, of course not, but it's easier in our calculator if we don't have this, right? Could we do that? Sure, you cancel anything you want as long as it's on both sides, right? Okay, we're just simplifying here. We're not doing any essential steps, but simplifying. Boy, this is looking a lot neater here now. Look at where we've got. A few minutes ago, you guys are telling me, oh, this is a hard question. I don't know where to go with this. Okay, you do. Now we'll see if you can solve this math-wise. Got an idea, Justin? Okay, cross multiply. I like that. So take the 0.35 minus r. Up by multiplying, take the r squared up by multiplying. Oh, that's nice, isn't it? Glad that's a 1, because then it makes one of those numbers disappear, right? 1 times r squared is just r squared. Hey guys, I got to be honest with you. First time I did this question, I looked at this and said, oh no, it's one of the things I hated most about math. FOIL. That's what I'm thinking. Anybody else kind of spot that? Yeah. I'm like, I hate doing that. But then I realized the next time I did this question, I made it a lot harder than I had to. Anybody see something easier than that first inside-outside thing last? Yeah. Do whatever you want, as long as you do it to both sides. Square it, I don't care. Cube it, I don't care. Multiply it by 13,127.2. As long as you do both sides by whatever that number was. Perfect. Perfect. What's the square root of 2.5? 1.67? Okay, 1.58 times, look at that. Square disappears. Square disappears. Now we're getting there. Home stretch. Home stretch. What next? What next? Yep.
Add the r out.
Yeah, well, I don't think we take that r out yet. Yeah. Yeah, let's distribute that. 1.58 times 0.035. What's that? You have that? Does anybody have that? Yeah. 0.593 minus 1.58r. So we're multiplying the 1.58 by everything inside those brackets. Equals r. Oh my goodness. We are so close to being there right now. Combine the r's, right? R plus 1.58r is, Tasia, what do you got for that? R plus 1.58r. 1r plus 1.58r. Good. 2.58r. And then divide, right? What do you get? I think it's like 0.21 or something like that. 0.21. Okay. 0.214 meters. Beautiful. Beautiful. R is 0.0214, 2.14 centimeters, right? What does that tell us? Tells us that charge number 2 has to be 2.1 centimeters to the right of charge number 1. How far away from number 3? Well, 3.5 minus 2.1. Got it?